Hey guys, this is your Unit 13, both A and B review video. Don't forget there is Unit A still available. I'll provide a quick link at the end of this video for you guys so you can refer back to it. Before I get started, I just want to re-emphasize how important it is to know your formulas for probability. Know what you're doing when you're proving independence. Know your conditional formulas. Know your ands. Know your ors. If you don't know that, you're going to have a difficult time with the test. So just make sure you review all those formulas and look over the front page of this packet. Now I'll just show you which ones I'll go through. 2, 3, 6, 7, 10, 13, 14, 23, just a few parts of it, 24, 25, 26, and then I actually pulled a question from the notes that I think would be beneficial to go through again, where we look at using z-scores to help us match scores on other tests. Okay, so starting just from the beginning, classify each of the following scenarios as having events that are dependent or events that are independent. So for part A, a person pulls a red marble out of a bag that has 5 blue and 7 red marbles. So keep in mind that's 12 total marbles. And does not replace it, meaning you do not put the marble back in. Then a person pulls another red marble out. Is the probability of pulling the second marble out dependent on pulling the first red marble? Explain. Rather than writing this out, I'll just explain that if you were to originally pull a red marble out of the bag, you have 12 originally, right? The probability of pulling a red marble is 7 out of 12. Now, if you pull out that marble and you don't put it back, you are no longer pulling from a total of 12 marbles. You're pulling from 11. Okay? Now, because you pulled out a red marble and you didn't put it back, you no longer have 7 red marbles in the bag. You have 6. So verbally what you would write is, yes, the probability of pulling a red marble is dependent upon pulling the first marble. So the second marble probability is dependent on the first. Because when you don't put the marble back, it changes the number of marbles that you're pulling out of the bag, or it changes the probability of the second marble. And you'll see that written on the answer key. But this is the math explaining it. Technically, what we're doing is the probability first of pulling a red marble times the probability, times the probability of selecting another red marble, given you had already pulled a red marble. This is your probability formula for an and when your events are not independent. Okay, meaning that this first one had an influence on the second one. Now let's just say, in theory, you did put the marble back. Then technically, it would have been 7 out of 12 times 7 out of 12. Because if you put it back, you'd have 12 marbles again, and 7 marbles again for red. And it wouldn't make a difference. This would be if it was independent. Because the second marble was dependent on the first, that's why it changed. And then you just multiply across. So what is that? 42 out of, I think, 132? Yes. Okay. A person flips a coin and notes that it comes up heads. Then a person rolls a 6 standard die and notes that it comes up with a number less than 3. Is the probability that the number came up less than 3 dependent on getting heads? So basically you've got to ask yourself, if you flip and you get heads, does that have any influence on how you roll a die? And the obvious answer there is no. The coin flip has absolutely nothing to do with you rolling a die. These are independent events. One thing is not going to have an influence on the other. It's not like since you got heads, you're magically going to get less than 3 more often. Okay? So these are independent events. So this means we just have to multiply them. Probability of heads times the probability of rolling a number less than 3. Okay, so heads is 1/2 of the time. Less than 3, that's 1 and 2, right? So that's 2 out of 6 options, which is 2 out of 12 when I multiply across, or 1/6. And coming back here again, these are your and scenarios where and is multiplying. This is independent, this is dependent. All right, there's a 34% chance that a person picked at random from the adult population is a regular smoker. I'll do probability, smoker is 0.34. 18% chance that a person picked has emphysema. Probability of emphysema is 0.18. If the percent of the adult population that are both regular smokers and suffer from emphysema is 14%, so S and emphysema is 14%, find the probability of being a smoker or having emphysema. Okay, so I just kept track of everything along the left-hand side here for us. Okay, so first thing I need to write down is my OR formula. They want me to find something out about this, so let's write it down. Probability of S or E, smoking or emphysema, is equal to the probability of both events separately. Take away the overlap, which would be your AND. Okay, because you got to figure, okay, this is the probability of smokers, this is the probability of emphysema. Likely there's some people that fall in both of these categories, and I don't want to count them twice. Okay, so I plug in my numbers, 0.34 plus 0.18, take away my overlap, oops, and I get 0.38. And it's as easy as that. Now, what we could do is use this formula, and what if I gave you information about the OR and I wanted the AND? Just call this X and then solve for it. So know your OR formula and understand that I could give you the information and then say solve for one missing piece of it, and you just have to solve for that correct missing piece. But what's really important is knowing how OR works. Skip over all of this. All right, let's go here. When an avocado is selected at random, I'm gonna move this a little bit. The probability that it is ripe is 0.12. The probability that it is bruised is 0.054, and the probability that it is ripe and bruised is 0.019. We're going to create a hypothetical 1,000 table below, meaning we pretend there's 1,000 avocados. Okay? So first thing they tell us is that we have 0.12 that are ripe. So ripe, that would be this column, times 1,000 is 120. We got bruised, which would be over here. That would be this subtotal, would be 54. And then 0.19 times 1,000, that's ripe and bruised. So that's 19. Okay, now just remember from part A, our two-way tables, all of our columns and rows have to add up to each other. So like I know this number must be 880 in order for these to add to 1,000. Likewise, this must be 946, and so forth. These add to 54. This must be 101, and lastly, this must be 845 for these to sum to 880. Determine whether or not being bruised and ripe are independent. Okay, you need to know this. It came up on the exam. I think it's come up at least twice now. You have to understand how to assess independence. So what you are doing is seeing, is the probability of being bruised, is that equal to the probability of it being bruised given it's ripe? That's your formula. It's not probability of bruise compared to probability of ripe. That tells you nothing. This is your formula. Okay? So first of all, probability of just being bruised is 54 out of 1,000 or 0.054. Okay, that one they actually told us. Now, the probability of being bruised, given it's ripe, okay, focus here. Given it's ripe, here's ripe. That means we're just looking at this column. These are all the avocados that are ripe. Of the ripe avocados, how many were bruised? 19 of them. Okay, so in my calculator, I do 19 divided by 120. Gotta move my calculator up a little bit. I get 0.158. Because these probabilities are not the same, they are not independent. And you're actually done. When it says justify your answer, this work is sufficient. I showed my math, I justified to the grader that these two probabilities are not the same, therefore they're not independent. Okay, so you don't have to write a sentence or anything, just show your math. You need to make sure you're labeling your probabilities though, so that we know exactly what you're calculating. Otherwise, we have no idea what your numbers stand for. Okay, going through information you can pull from your calculator. Let's say I've got these scores between 5 and 45, and these are your frequencies. Pull my calculator real quick. Okay, remember how you enter stuff into a list. You hit Stat, Edit. Now if you have stuff in your calculator list like I do, all you have to do is highlight the column, hit Clear, and then Enter, and that'll clear it all out for you. Keep moving this around. Okay, so I'm going to just start entering stuff. So this will be my L1, just so you know this is L1. My L2 will be my frequency list, so I don't have to enter, 15 times in the calculator, because that's just time consuming. Okay, good. Everything matched between my L1 and L2. So now if I want to get all those statistics, I go Stat, Calculate, 1var stats. And what's really sad is, unfortunately, my calculator simulator doesn't have the updated software, and I don't know how to update it, or if it's even possible. So I have to do this the old school way. I have to type in L1, comma, L2. So if you have an older calculator that doesn't have the update, although hopefully we've updated you, this is what you'd have to do. You're telling the calculator to look at L1 and L2 for both the data and then the frequency. And then I hit Enter. Yeah, I don't know what happened to my stuff back here. I'll grab that in a second. All right, so this first number, X bar, that's your mean. This thing that you're seeing with the little Greek symbol with the 9.812, that's your standard deviation. I have 75 data points. And then the min, quartile 1, median, quartile 3, and max, that's your 5-number summary. There it is. Okay, and then that's what you would plug in here. So, okay, so 30.2. Her median was 30. Standard deviation 9.81 or 9.8. All right. Min was 5. Max is 45, which you can even see that here. Quartile 1 was 25. Quartile 2, or the median, is 30. These two things are the same. Quartile 3 is 35. Interquartile range is Q3 minus Q1. So Q3 is 35, Q1 is 25. So our interquartile range is 10. Our range is max minus min. So that's 45 minus 5, which is 40. And lastly, our mode happens the most. Looks like 15 times, so that means 30 is our mode. Now, if you had a larger standard deviation, that would mean the data would be more further spread from the mean. Standard deviations, your typical distance, your data points lie on average from the mean. All right, and now we get into some normal distribution stuff. First of all, just remember when we introduced you to standard normal distribution. Standard, this is not related to this. Standard, whoop, that's not how you spell standard. Standard normal distribution is if you had data that was approximately normal, looks like that, and the center of the distribution 0 and the standard deviation's 1. Okay, in which case then along the bottom, each of these are what are called z-scores. So -1 would be a z-score, 1 would be a z-score, and that would tell you how far you are from the mean. So if you had a z-score of 2, you are 2 standard deviations above the mean. If you had a z-score of -1, you are 1 standard deviation below the mean. Okay, so what makes this standard, this distribution standard, is that the mean or center of the distribution is 0, and the standard deviation is 1. Now, thankfully, because not everything in life is standard, the calculator does a lot of the computations for us when the mean isn't 0 and the standard deviation isn't 1. But it's important to understand the standard normal curve to know what z-scores mean and all that fun stuff. Okay, so we're going to start off with a normal distribution. It's non-standard because the mean is 16 and the standard deviation is 6. Okay, so this is non-standard. I want to find the percent of data that would fall or have a score, so whatever, that such that it's greater than 16. So I'll draw a sketch. Mean is 16, standard deviation is 6, and I want it to be greater than 16. Okay? Greater than 16 means you're shading to the right. Now, I'll do it both ways. Theoretically, if you are greater than the mean, means the center of your distribution, 50% of your data lies above it, 50% lies below. So technically, the probability of getting a score greater than 16 is 50%, or 0.5 for the probability. If I do this in my calculator, I think I get like 0.4999 for whatever reason, but that rounds, okay? So I do second vars option 2. Now again, because I don't have the update, I have to just show you what it would end up being. You'd have a prompt screen that would tell you lower bound, and our lower bound would be the 16, comma. Then it would say upper bound. This is what I typically write as 1E99 for the calculator code for like positive infinity. It's like a really big number, but pretty much you can just hit a bunch of 9s. Really big number is your upper bound. The next number is your mean. And then your standard deviation. Lucky for you guys, or at least most of you guys, hopefully, you have the prompt screen so you don't have to remember the order of those numbers. And I hit enter. Okay, now obviously you see it's 0.499999, but that rounds to 0.5. Okay, now what if I want a score that falls within 10 and 22? So if this is 16, we're looking between 10 and 22, so something like this. We're looking for this area. Oh, and one other thing, make sure when you type it in your calculator, you show your work. Okay, so normal CDF, second vars option 2. My lower bound is 10, my upper bound is 22. Mean is 16, standard deviation is 6. And then this is what you'd write on your paper so that we know what you're plugging in your calculator. Enter. Okay, so 0.682 or 6.683. Okay, 3 or 4 decimals. So my work, again, that I would write down on my paper for a test is normal CDF, 10, 22, 16, 6. And then that's what corresponds to that answer. So again, what that means in this normal distribution is the probability of randomly selecting something, whatever we're looking at, data value, and it falling between 10 and 22 is about 68%. Lastly, we'll do one where I have to be less than 1. It's going to be small. So this is 16. Less than 1, that means we're shading to the left. Now your lower bound here is going to be negative infinity. So I'll write second bars, option 2. I'll write negative 999999999. Okay, so a really big negative number is sufficient. Our upper bound is 1. Mean is 16, standard deviation 6, so 0.006. Okay, so what I'd write on my paper is normal CDF. You could really either write negative 9999999, or I write usually negative 1E99. That's my code for negative infinity in the calculator. Upper bound is 1. Mean, standard deviation, and 0.006. So the probability of selecting a score and having it being less than 1 is less than 1%. It's not happening very often, or, not happening often at all. Probability of it occurring is small. And that's your work with normal CDF. So just make sure you show your work. If it asks for a sketch, draw a sketch, although I always draw a sketch. And yeah, you have a prompt screen. If for some reason you didn't get your calculator updated, you just have to make sure you remember the order of the numbers, and then you'll be fine. As you can see, it's completely doable. I just had to remember the order. But hopefully we updated you. Okay, so now we're here at 13. The average weight of full-grown beef cows is 1,470 pounds with a standard deviation of 230. If the weights are normally distributed, what percentile rank of a cow? What is the percentile rank of a cow that weighs that much? All right, so you got to figure. You got your normal distribution. Mean is here. And then you got a cow way up here. I want to find out what percentile rank this is, which is the percent that they are as heavy or heavier than. So with that being said, we want the probability of randomly selecting a cow and it weighs less than that. So we're always shading to the left anytime we're looking for percentile. Okay. So this is a normal CDF problem because I'm finding the area under the curve. My lower bound is negative infinity. My upper bound is 17 number. Mean is the 1470 number, and standard deviation is 230. And then I just plug it in my calculator. And there you go, so 0.888, which is approximately the 89th percentile. Okay, so what that means, again, in the context, is that the cow that weighs 1,750 pounds is heavier than, or as heavy as, 89% of other cows. On average. All right, and then 14. The prices of printers in a store have a mean of 240 and a standard deviation of 50. The printer that you eventually choose is $340. What's your z-score? Okay, so z-score is calculated by your score, take away the mean. Should I write it like this? Take away the mean divided by the standard deviation. Okay, so your printer was $340. The mean is $240. So it's your difference from the mean, and that's going to end up being a positive number there because you're above the mean, divided by the standard deviation of 50. Because we want to find essentially how many standard deviations you are from the mean. That's what a z-score does. Okay, so 340, take away 240. Oh, I could have just done that. 100 divided by 50 is 2. So it's a positive 2. That means you are 2 standard deviations above the mean. Okay, so z-score and b, like those are the same thing. When you find the z-score, that tells you how many standard deviations you are either above or below the mean. Z-scores are useful in data because that's how we can compare data with different means and different standard deviations. This is actually a good segue into that problem from our notes. So I'm actually going to scroll ahead. And look at this problem, because this really goes on why we use z-scores or how we can use z-scores to help us compare data for 2 different tests. We have 2 versions of the SAT, the April version and the May version. The April version shows a mean of 480 and a standard deviation of 24. The statistics for the May version show a mean of 510 and a standard deviation of 20. Sloppy writing, sorry about that. Assume the scores are normally distributed. Maria took the May version. In what interval must Maria score to claim she scored as well as Joanne? Oh shoot, I accidentally deleted the part where I found out how well Joanne did. 1 second. Okay, I found it. Joanne scored between a 510 and 540. Whew, alright, and she took the April version. So, when you want to match another person's score, you are looking to be as many standard deviations away from the mean as your other person was. So I want to find out how many standard deviations Joanne was from the mean on her test, and then Maria just has to be the same number of standard deviations away on her test. Okay, so let's start with Joanne. Essentially what I'm going to find with Joanne are her z-scores. Since she gave us an interval, there's going to be 2 of them. So her verse z-score was her 510, take away the mean of her test, which was 480, divided by the standard deviation of her test, which was 24. Her second one, similar format, just now this 510 is now going to be a 540. That's not right. What did I do? Oh. Sorry, this is supposed to be 30 divided by 24. Okay, so 1.25. Okay. So what this work tells me is that Joanne's test score was somewhere between 1.25 and 2.5 standard deviations above the mean. So Maria needs to be the same number of standard deviations above the mean on her test, which was a 510. Okay, so here's Maria. So she needs to match these z-scores. So she's got to match a 1.25. She's got to match a 2.5. I don't know her score. I'll call her lower bound x. Okay, so her lowest score as x, the mean on her test was a 510. Standard deviation was 20. I'll call her upper possible score y. Okay, and now you just got to solve for x and y. So put them over 1, cross multiply, and solve. So let's see here, 1.25 times 20. Then I'll add over the 510. Okay, so 535. And then 2.5 times 20 by cross multiplying, add over the 510. Obviously you'd show your work here, but I'm just kind of doing it in the calculator and then writing it for you. So 560. Okay, so this means that Maria needs to score between a 535 and a 560 on her SAT to then claim that she did equally as well as what Joanne did, because she then technically scored the same number of standard deviations above the mean on her test that Joanne did. Whew, I feel like everything I say in this video is a mouthful. Alrighty. Alright, so it looks like the next problem I was going to do is 23. I already filled in the table because you guys are good with that. Everything just needs to add up. What percent of boys play sports? Saying of boys. So that means we're only looking at the boys. Of the boys, 18 play sports. So 18 out of 22. Or an equivalent 0.818, okay? Which is then approximately 82%. Now, is this joint marginal or conditional? Conditional means you're taking a cell from the middle of the table and dividing it by a subtotal, which is coming from the margins here. Because we're only looking at a portion of the table, this makes it conditional. How many boys play sports? Okay, so just looking at your table, this is boys, they play sports, your answer is just 18. This is a joint frequency because it's just a single cell from the middle of the table. If it was a joint probability, I would phrase the question as, what's the probability of randomly selecting a student, so that's out of the whole 43, and they're a boy that plays sports? Then it would be 18 out of 43, and that's what's considered a joint probability. In this case, it just says how many, so it's looking for a number, not a probability. So then that's why it's 18. Okay, and then last thing, if the student is a girl, whoops. Okay, so if the student is a girl, that sounds like a conditional, so I'm only looking here. What percent of them play sports? So that's 11 out of 21. Okay, and then that would be an equivalent 52% approximately, and that's also going to be conditional. Okay, I'm going to do one more here. How many students surveyed play sports? If I go to play sports, there's 29 students. This is considered a marginal frequency. Frequency, it's just a number, because the margin told us the answer. 29 as a subtotal. If I said, what's the probability of randomly selecting a student and they played sports, then it would be 29 out of a total of 43. And that's still marginal, but then it's a marginal probability. Either way, your answer is coming from the margins. All right, and now we're getting into something a little different here. Find the score for a person in the 10th percentile on the SAT, given the mean is a 1050 and the standard deviation is 150. So you have to think, you got this this normal distribution. The center of it is a 1050 and the standard deviation is 150, and you're at the 10th percentile, which isn't that great, to be honest. So if you're at the 10th percentile, means you're kind of low down here. I want to know what this data value would be in order to be at the 10th percentile, which means you scored better than or equal to 10% of people that took that same test. Now, we don't know the data value that will give us this, so we're not using normal CDF here. We know the area. The area to the left of this value must be 0.1. The area under the whole curve is 1.0. This is 10% of it, okay, because that's what corresponds to the 10th percentile. Since we know the area, we're going to use inverse norm. Normal CDF is used to find the area. Inverse norm is if you know the area and you're working backwards to find the value that gives you it. So in inverse norm, it'll ask you for the area first. I'm just going to write down what your prompt screen would say. And the area, I'd type in 0.1. It'll ask you for the mean. And in this case, it's 1050. And then it'll ask you for the standard deviation. And you just type this in. Unfortunately, again, I got to do it the old school way. So let's see. Second var is option 2. Whoopsies. Sorry, option 3, excuse me, inverse norm. So I have to just plug it in that order. 0.1, 1050, 1050, enter. That cannot be right. Oh no, that's right, never mind. Sorry, because I forgot we're on a really high test. Good, so 857.76. So again, this is your calculator work that you would write down. Okay, and then we give you rounding directions here, but we'll say, just for sake of, a couple decimals here, this means that this is the data value that would put you at the 10th percentile. You scored an 857. Okay? Okay, and one more thing before I move on. Know that inverse norm, when it asks you for the area, it's always, always, always the area to the left. It'll never be to the right of it. Okay, Jeremy, let's see, we got the SAT taken by most high school students in a recent test. The SAT mean score was 1030. Jeremy is planning on taking the test. If the mean is still at 1030 and the scores have a normal distribution with a standard deviation of 120, what is the minimum score that Jeremy can get to be in the top 15%? So this actually relates to what I was just saying. We don't know the data value, so that means we're going to have to use inverse norm. Okay, the middle here is a 1030. Top 15% would be here. Don't know what it is. Put a little question mark. Here's your top 15. Top 15%. Now, like I was just saying, when you use inverse norm, it's always the area to the left of the value, which if the whole curve is 1.0, this must be 1 minus 0.15 or 0.85. Okay, so when we plug this in our calculator, it'll be inverse norm. I can't spell. I mean, I can. It just kind of blends together there. The area we'll plug in is 0.85. If you do 0.15, you would end up way down here, so be careful. It's 0.85. Mean is 1030. Standard deviation is 120. Okay, so this says to the nearest tens place, not tenths. Tens would be right here. 1150. Okay, so that means he must score an 1150 on that test to be considered to be in the top 15%. Okay, what's his z-score? Remember, z-score is your score. Take away the mean. Divide by the standard deviation. And that actually works out to be a nice 1. So that means he is 1 standard deviation above the mean. All right, and then last thing we'll talk about is just shape and center. This first curve you see, you can draw a nice smooth symmetric curve over it. If I had to describe its shape, I would call it approximately normal. Or you could write approximately symmetrical. That would be fine. You could say it has a single mound. If I want to say its center, that's the balancing point. Where do you think the data would balance? And it looks like it nicely balances at this 70. Okay. Now, when you're looking at a normal distribution, the center of it is the mean, or the average of all of those scores. It actually would also be the median, but we'll say the mean would be the center. If you look at a skewed distribution, like this guy, if I draw a curve here, it's clearly not symmetrical. Because the tail is on the right, this is what we called a skewed right distribution. Okay, so this would be how I would describe the shape. The center of it, the balancing point, looks like maybe it would be somewhere like right in here, maybe at, I don't know what that is. I was just going by 5, 10, 15, maybe like 15. Okay, and that's not the mean anymore for the center of the distribution. That's actually the median. That's your middle value. The mean would actually be somewhere in here, okay, because these data values to the right of it would be pulling the mean into the tail, and that's why we call it skewed right, okay? But the center of our distribution, the balancing point of it, the nice center, we'll say is about 15, and technically that's the median, the balancing point, when we're looking at a skewed distribution. Okay, so when you're describing a normal distribution, the best center to use is the mean, but if you're describing a skewed distribution, you're actually using the median to describe the best center of the data. And I think I did everything I said I was going to do. Yeah, that's it. All right, so a nice 41-minute video. That was a mouthful. Hopefully it was all you needed, so good luck studying.